Hello everyone, welcome back to our next installment of integrating stuff. Today I want to make a quick video and talk to you about what is called the average value of a function. In calculus, average is going to be the same thing as it has been, but when you are talking about an infinite number of values, average, the calculation, takes on a little bit of a different feel, if you will. So remember, in calculus, we're always talking about infinite numbers of things, and they're usually infinitely small increments and all that good stuff. All right. So what we want to be able to do when we say an average value, what we really mean is an average y value. So what we want to be able to do is say, okay, for this function, and it went from, in the interval where from 0 to 3, I want to know what was the average y value on that interval. And that will become useful to us in all kinds of word problem type situations. So we know from algebra, or even before that an average, also known as a mean, right? Everybody always remembers that word. That'll come back in a minute. Average, mean, average value, mean value. I smell a theorem. If I want to find an average, I add all the stuff up and I divide by the number of values. Okay. Now again, we're talking about an infinite number of y values. And so if you added up an infinite number of things, that would probably also be an infinity, which is an infinity over an infinity, which is an indeterminate form. Okay, so don't worry. We have calculus and we have a different way of adding stuff up. Okay, one of the ways that we have in calculus of adding stuff up is to take an integral. Remember, integrals are all about an accumulation, right? It's an area under a curve. So if you take the area under an xy curve, what you get is basically the adding up of all the y values. Right? If I want the number of values, well, again, that's an infinity, but we can mimic that by just using the width of the interval. Okay, so if you want the average value, and again, the y there is implied, it's the average y value of a function, what we're going to do is we're going to take the integral, and then we are going to divide it by the interval width. Now the definition looks a little more complicated than that because there's fractions involved, right? So here's the definition of the average value of a function. Allow me to move my photo here. Okay, AVF, this stands for average, right? So the average value of a function, this is oftentimes how we see it in books. I just write average value. Here's my integral. Again, this is my total, right? My total of my y values, whoops, sorry. My total of my y values is going to come from my integral. It's going to add them all up. And then instead of a number of values, we're going to just divide by the interval width. And again, it's written here as 1 over out front because the other option would be to write a fraction that has an integral in the numerator and then b minus a in the denominator. And if you want to write it like that because you're thinking average, so added up all the values divided by the interval width, that's fine too. Generally, the way we see it seen is with this out front. So we see lots of questions that are literally as straightforward as find the average value of this function on this interval. And we just have to know, again, this rule of how you do it. It's an integral divided by the interval width. I'm going to try really hard not to mix up the words integral and interval. Let's see if I can do it. Okay, so here we have a parabola, 4 minus x squared, and we want to find its average value on the integral from, that didn't take long, on the interval from 0 to 3. So on this interval from 0 to 3, we can see that the y value starts up here at 4. And by the time it gets to 3, it's down here in the negatives. So I need to take all the y values between 4 and way down here in the negatives at -5, it will be, add them up, and then divide by the interval width. What I want is the average. In other words, if I want to find the mathematical middle between this high point at 4 and the low point at -5. Okay, so I need to set up my integral. So I need to find the integral from 0 to 3 of 4 minus x squared. That's going to add up all my y values. And then I need to divide it by the interval width, which in this case is 3. So I'm going to put a 1/3 out front because that's the same as dividing by 3. All right, I'm not going to lose my 1/3 when I evaluate this integral. So don't even think I'm going to. All right, let's integrate this. So the integral of 4 is 4x. The integral of x squared is x cubed over 3. And I am evaluating that from 0 to 3. Okay, so I have 1/3 and I need to put my 3 in here. So that's 12. 3 cubed is 27, divided by 3 is 9. And then minus, I have my 1/3, and when I plug a 0 into here, I just get a 0. Okay. So here I get 12 minus 9 is 3, 1/3 of that, I just get a 1. So what they're telling me is that my average value, the average y value, is right here at 1. Okay. And again, notice it's kind of in the middle, right? So I've got, it's more on the positive side, but that's okay. All right, so the next question is, does f ever assume its average value? And notice, obviously, yes, the function does, right? Okay, so the average y value is 1, and indeed, f does assume its average. Now, I don't know if you remember our friend, the mean value theorem. The mean value theorem for derivatives said that if you take the average slope over some interval, take the average slope at some point on this interval, you're going to have a tangent line that exactly matches that average. In other words, the slope over an interval at some point is going to take on the average slope over that interval. Okay. The mean value theorem basically tells us that functions always take on their average at some point as long as they're continuous. So we talked about derivatives and it taking on the tangent or the derivative slope taking on the average slope or the secant slope. This is the same thing now, except with integrals. I found out what the average y value is. So this may even make you think of our friend, the intermediate value theorem, right? That if this function went from 4 to -5, it had to go through every value in between, right? So sometimes I feel like this theorem is a little bit redundant in that way. Because if it went through every value in between 4 and -5, obviously it went through 1. But also, its average would have to be on that interval. Right? How would its average not be on the interval between the highest and the lowest point? So it's kind of like a marriage of mean value theorem and intermediate value theorem for integrals. So it's always going to take on its average. And that's what our friend here says. So it says the mean value theorem for definite integrals. So as long as f is continuous on a closed interval, then at some point on that interval, the function is going to exactly match its average value. So this is the average value of y. That's my average y value. And we're saying that at some point c is just a number on the interval, somewhere between a and b. This is the y value at some point, which we're calling c, on a to b. So at some point in there, the y value is going to take on its average y value. Okay, so I want to show you some cool stuff that flushes out of this. Okay, oh, here's my little translation. Let me move my floating head again. Continuous function on a closed interval. Remember, that always has to be continuous on a closed interval, or you better not be using any of these theorems. Okay, always, always, always assumes its average value, and notice it says at least once. So same thing before with the intermediate value theorem. I know it went from 4 down to -5. I know it went through all those points in between. What I don't know is if it went through more than once, like, right? Like a function could dip down and come back up and dip down and come back up and pass a certain value several times. The value theorems are promising that it does it at least once. It might do it more than once. We don't know. Okay, so I want to look at some cool stuff that happens with average value. All right, so the first thing we want to do on this particular slide is find the average value of this function, x squared plus 3, on the interval from 0 to 3. So let's take a moment and do that. This is a great place for me to be, right there. Okay, let's find the average value of f of x on the interval from 0 to 3. So let's set up our integral, okay, that I need to go from 0 to 3 on the function x squared plus 3. And then out front, I'm going to multiply by 1 over the interval width. In other words, I'm doing my integral from 0 to 3 and then dividing by 3 because 3 is the width of my interval. Okay, so when you set that up, take a moment. Hopefully, you got that integral is equal to 18. Right? This integral, when you evaluate it, is equal to 18. So my average value is 6. It's 1/3 of that. Okay. Now, did you do that integral on your calculator or did you do it by hand? I'm curious. All right. So here's 6, right? I'm going to put a line here at 6. This is my average y value. So as I go from 0 to 3 on this interval, my y value goes from 3 up to 12, and there's its average right there in the middle at 6. There's my average, because of course it was increasing slowly as it goes, right? So my average value is somewhere in between my low point, which is 3, and my high point, which is 12. So does the function take on its average value? Yeah, it sure does, right there. Okay, but there's some other cool stuff that happens with this theorem that I have not really seen come up AP-wise as far as like them asking direct questions about it, but I think it's kind of neat, so I'm going to show you anyway. Okay, so the value of the integral has to take on its average. Okay, so the actual value of the integral has to take on the average as well. So watch this. I can go at some point in the interior here, I should be able to take the integral from 0 to b and get 6. Okay, well, obviously. All right, so again, I don't know if this is brain-busting material. All right, so if I take the integral of this function, I'll evaluate it from 0 to b. I'm saying that has to come out to be 6 at some point along the way. Yeah, okay. That point is 1.57, so right here. Okay. So if I only go to 1.57, this will take on a value of 6. Okay, what I think is the more fun one, the more interesting one, this is my favorite. It's this fun fact. If you take a rectangle, if you create a rectangle that is the width of your interval, so in this case it will go from 0 to 3, and has a height of your average value, it's equal to the integral. So one rectangle, think RAM, right? It's going to be not technically an MRAM, right? But it's going to be the height of the rectangle is going to come from the middle of the interval because it's going to come from your average value. So you do one RAM, you do one rectangle RAM, whole width of the interval, and the height of the rectangle, instead of using the left or the right or the middle, we use specifically the average value. So in this case, we would use 6. It equals the integral exactly. Okay, so again, look at my beautiful rectangle here. If I go from 0 to 3 and I make the height of my rectangle match my average value, my average y value, it pops out. Look at this rectangle. It is 3 by 6. It is 18, and that is exactly, whoops, your quiz isn't today, relax. And that is exactly the width of my, or I'm sorry, not the width of my integral. That's exactly the value of my integral. So I think that's kind of a fun fact. And again, it's not something we see directly asked about, but it's pretty neat. So I think math is fun. All right, so that's it for the average value. Brace yourself because we're going to be doing more and more and more integrals as it goes. I will see you soon.